Hello and welcome to Confidence Intervals Challenge Problems. So today we are focusing on challenge problems. All that means are just problems that ask the question a little bit differently or use only part of the formula as opposed to the whole formula and kind of measure if we understand all the pieces of the formula and what those pieces mean as opposed to always using the whole formula. So let's see what that looks like. So just to review, our steps on how to construct a confidence interval are to state, plan, do, conclude. So we focused a lot on state. We should be really confident with population and parameter. Plan, we're going to talk about normal sampling distributions, specifically today for example 3, but we're pretty confident in our conditions. The do step is where we're going to be spending most of our time today, specifically part of the do step called the margin of error. So how do we calculate confidence intervals? So all intervals, no matter what they're talking about, means or proportions, one statistic or two statistic, they all follow this form. The point estimate, which is just the statistic or the sample data, plus or minus this big piece called the margin of error. This is where some of the challenge problems get their material from, because the margin of error, we said, is different for different types of intervals. So the formula changes, and we want to see, do you know which margin of error formula to use, and do you know the specific pieces of the margin of error and of the formula? So let's take a look at the two formulas that we've seen so far. This first formula is for means. And for means, we said that's x bar plus or minus t star, which is my critical value, times the standard error, which is s over the square root of n. So the critical value is the star piece, and then the standard error is s over the square root of n, or everything after the critical value. So for proportions, we have p hat. So for proportions, we have p hat plus or minus z star. For proportions, it's always z star. So proportions always is z star, means sometimes it's t star, sometimes it's z star, like we're going to see in a minute. But then we have z star times the standard error, and this entire piece is the standard error. The standard error is just a fancy word for the standard deviation of the sampling distribution. So standard deviation of the sampling distribution is the same thing as standard error, and it's these two formulas that we've been working with for a long time. So how they could kind of throw that in there as a challenge problem. So example 1 says the weights of 9 men have a mean of x bar equals 175 pounds and a standard deviation of s equals 115 pounds. What is the standard error of the mean? I can guarantee you if this is a multiple choice question, this is going to be one of the answer choices, 15 pounds. But 15 pounds is the standard deviation of one man, but we have a sample of 9 men, so n equals 9. The standard error is s over the square root of n. So we can look back to my confidence interval formula. Standard error is s over the square root of n, which would be 15 over the square root of 9, which gives me 5. So the standard error for this group of 9 men that we're weighing is 5 pounds. And you could say pounds in there too, or if it's a multiple choice question, it may just say 5. So this is one example of standard error. This is for means. Let's take a look at example B, because it may be for proportions. So it says an SRS of 50 students at a large middle school are asked, do you have a television in your bedroom? 28 of the students responded yes. If P hat is the proportion of students who answered yes, what is the standard error of P hat? So it's asking for the standard error. If we look back for proportions, the standard error is the square root of P hat times 1 minus P hat over N. Well, I know that N equals 50, but P hat isn't given to me in the problem. It does say that 28 of the 50 students responded yes, so 28 over 50 is my P hat, and that's 0.56. Leave that as a decimal. Don't change that to a percent, because I'm going to take that decimal and throw it into my equation for P hat. So I get the standard error is 0.56 times 1 minus 0.56 over N, which is 50. And that gives me a standard error of 0.0702. So this is my standard error for proportions. Also, these numbers should make sense. If I think about the standard error, that's how far off might I be with each sample. Well, being off by 5 pounds makes sense for 175 pounds. That's a kind of normal number. Being off by 7% is normal for 58%. So if you're getting a number right here of like 39.7, that's saying 3,970%. So think about, like, do these numbers make sense? For proportions, the standard error is always going to be a decimal, and usually it will be like 0.0 something or 0.1 something, because you can expect to be off by, 7%, 10%, something like that. For means, just think about, does this number make sense in light of that number? So let's take a look at example 2. This is going to deal with the margin of error in kind of a different way. So it says you want to estimate the mean fuel efficiency of Ford Focus automobiles with 99% confidence and a margin of error no more than 1.5. So I'm going to write that over to the side. My margin of error has to be less than or equal to 1.5 miles per gallon. So preliminary data suggests that sigma equals 2.4 miles per gallon is a reasonable estimate for the standard deviation for all cars of this make and model. How large of a sample do you need? So we want to know, what does N need to be? So before we go any further, we're going to add a little kind of do part of your notes. These notes say if sigma is given, so if sigma is given in the problem, then my formula that I'm going to use is x bar plus or minus z star times sigma over the square root of n. This formula, this kind of little addition, is only used when you're looking for n. So these problems are very rare, except when it says how large of a sample do you need, because it has to give me sigma in order for me to use z star. If we think about t star is dependent on n. N. So I can't find t star unless I know n. So if it doesn't give me, if it does give me sigma, I use z star in this formula. So back to the problem. That's a little side note. Back to the problem. If I want to find how large of a sample do I need, I'm going to set my margin of error, which we know is z star times sigma over the square root of n, less than or equal to 1.5. It wanted a margin of error of no more than 1.5, so this entire margin of error piece has to be less than or equal to 1.5. So now when I go to plug in my pieces, z star for 99% confidence is 2.576 times sigma of 2.4 over the square root of n, because I don't know n, less than or equal to 1.5. So essentially, I just plugged in 3 of my pieces into my 4-piece puzzle, and now I'm solving for the missing piece. So if I multiply 2.576 by 2.4, I get 6.1824 over the square root of n is less than or equal to 1.5. Well, now if I'm looking for n, I want to cross multiply n to both sides. So if I times the square root of n on both sides, those cancel, and I get 6.1824 less than or equal to 1.5 times the square root of n. Got to get n alone, so divide by 1.5, divide by 1.5. And I get 4.1216 is less than or equal to the square root of n. So last but not least, to get rid of my square root sign, I square both sides, and I get 16.988 is less than or equal to n. Well, if I think about n being a sample size, I can't take 16.988 cars, so I'm going to round up to 17 is less than or equal to n, or I need at least 17 cars. So I need at least 17 cars, n is greater than or equal to 17, in order to have a margin of error less than or equal to 1.5. The last example and last type of challenge problem are where it's going to give you different graphical representations. It may be a dot plot, a stem and leaf plot, a histogram, a box plot, any type of graph, and you're going to have to defend whether or not it's normal for the sampling distribution, or if you can check off that normal condition. So let's take a look at example A. Example A gives me a dot plot, and this dot plot is very skewed to the right. But the sample size is 30. And we said if n is greater than or equal to 30, we can apply the CLT. And if we can apply the CLT, then it's normal. And that's checked off. So all you have to do for these is kind of look and see, does this graph follow a normal pattern? If yes, it's normal. If not, look at the sample size. If the sample size is greater than or equal to 30, we can apply the central limit theorem, which says it will have a normal sampling distribution. So A is a check because n was greater than or equal to 30. B, if I look at this stem and leaf plot, it looks skewed right as well. So the graph is not normal. And since n is equal to 12, it's not normal. Since this is not greater than or equal to 30, I cannot apply the central limit theorem, and the graph is skewed to the right, so both the graph and the sample size tell me it's not normal. So not normal, Last one, C. If I think about the graph for C, if it was normal, it would look more like this. So this graph shows that it's also skewed to the right. but my sample size is 45. Since n, or my sample size, 45, is greater than or equal to 30, I can apply the CLT. Therefore, the sampling distribution is normal. So these are 3 examples of showing how we can look at the graph or my sample size to determine if something is normal or not, and if that normal condition is met. So that's a wrap. We can use the margin of error to determine the sample size needed, and the standard error is the standard deviation for the sampling distribution, and there's a different formula for the standard error depending on means or proportions. So this is section 8.3 in your textbook. Please go there for more examples, and you'll see that there are several homework problems assigned from this section as well. Thanks, and I'll see you next time.